Thank you very much for this nice introduction. It's a little bit an exaggeration that I'm a co-author of the book, or you have to take into account that there are about 30 authors in the book, so it's a lot of chapters by many people. Some of them are sitting in this room. And from the introduction, I understand that my biggest task is not to tell the content of my slides, but try to keep you awake, because some of them will not be very easy as a background material for it. Anyway, I think I will have to give a number of different comments as an introduction, also about the title, Kinetics and Dynamics. I think I will have to explain this. We had a little bit of a discussion of that one with Jan Lin when the chapter of the book was prepared, whose content will be presented here. And here's what you see here is, of course, something totally known, not new. Molten salt reactors are different in many respects. What I think the novelty, or I hope the novelty of what I'm going to talk about is to show the same thing from a slightly different point of view, or in a different aspect, actually rather limited aspect, beyond what you already know, that there everything is different in an MSR. So this is what I tried to show through the content of the slide. And it, as the last line says, solutions in simple models give insight into the physics. That is the motto. I will use an utterly simplified model, which definitely has no connection with a real reactor. And by the way, also the subject I'm going to talk about is this kinetics, dynamics, and neutron noise, is something which today is not so very important or significant, when we still do not have operating commercial molten salt reactors. On the other hand, it is good to think of the certain aspects already in advance, as I try to interpret, before we fix all the design constraints on a reactor, when we cannot change anything and cannot put in new sensors. And then, of course, there will be results which show the difference in a complementary way to what you have already seen. Also, some questions which yesterday were already taken up, and I'm very happy to see those gentlemen coming in, because one part will be related to the question they took yesterday. So here is very short content. I will give a definition of the model used, and take the static and time-dependent equation, and then discussing the non-adjoint property, constructing the adjoint, and then also taking this very, very much simplified neutronic model. I have to add from the beginning, there will be absolutely no feedback in what I'm going to talk about. It's only neutronics. So only for this reason, you could already question how one can talk about dynamics, and I tell you why I think that's dynamics. And the dynamic equations in the frequency domain. I will tell you why this is interesting, why neutron noise is interesting, or at least try to illustrate. And calculate the Green's function and point kinetic approximation. That was something coming up yesterday. And as it was already, I already told that this material is from this book. Jan Lin already showed both the book and the front page. This is the front page and the back page together. Now, before I take the next slide, okay, the next slide is still innocent, so to speak, because that just shows the model, and in an even more simplified form, as in many of the slides yesterday. You see, it will be a one-dimensional model. It doesn't look one-dimensional because there is a loop, but in the equations there will be one space variable. It's a one group and one delay neutron diffusion model without any feedback, as I say, only neutronics, nothing else. And what I hope will be interesting is that even in such an very simplified model, there are some surprising aspects which can be interesting to look at. Now, I'm still hesitating to take the next slide. Some people saw my slides and they were kind of a little bit put off, because it was like flooding with equations. And that's what I'm going to show in the continuation. But the comments I want to add is this. That, first of all, what I usually tell to the students when I have a course on transport theory or even noise theory, that everything I'm talking about is actually absolutely simple, much simpler than it looks like in the equations. They might look messy, But that's not because they are complicated. It's just because there are several variables, there are boundary conditions, and so on. You have to keep them in mind, but it's not very deep in a certain sense. I mean, at least in the mathematical manipulation sense, those are very simple. And that's one of the points that I prefer the method when whenever you solve an equation, you also think of it, what it means, what are the conditions under which it's working, and what are the what is the interpretation of the results. The second thing is that although these models are not faithful to reality, on the other hand, even if they, as I said, look messy, the thing is that that's all there that is. So that you see the equations and you have everything. Now, when you look at a paper or listen to a talk in which there are very detailed calculations about a realistic problem, then of course the results are faithful. They can be used for designing a reactor. But on the other hand, you cannot go home and reconstruct them, because you need the code. You need to know how to run the code. You need to know under which circumstances the code is valid. If there is something not corresponding to intuition, then it's not very easy to find out why. Whereas in the equations which I'm going to show, there is nothing behind. That's just there it is. And still you can say that when you look at some of these messy things is that, but still I don't see the woods from the trees. And I will show the equations, but I will try to show you the woods without chopping the trees. And the trees you can look at home. So I have them in the slides so that it will be accessible after the course. But right now, you just will be confronted with them without, I won't explain the meaning of all of the terms and so on. Okay, so here, this is the model. There is a one-dimensional homogeneous, in addition, reactor, so there is no space dependence in the static case. When I'm talking about neutron noise, then there will be time-dependent and space-dependent fluctuations which will propagate and so on. So later on, there will be some small deviations. But in the model, so we have a core, and I will, to make it even more messy, two different coordinate systems. If you look at it here there is a model when the reactor is between the center of the coordinate, the zero of the beginning of the coordinate system is in the middle of the core, so that the boundaries are symmetrically distributed, and that's suitable for certain purposes, and in some other purposes the reactor will be between 0 and h, which is the width. Otherwise, there will be a loop which is not considered. It's just taken into account through a boundary condition. So that's why the model is one dimension. It's the only thing which we consider is this here. And of course, the velocity is not the same in the outer loop and in the core, but it's just a matter of scaling. So you can define an equivalent length in which the transit time will be the same with the given velocity, the same velocity in the core as if it was if there was a different length and a different. So that's it. So this is the setting. So there will be a transport time in the core, TC, and a transport time in the loop, and there will be a total transport time, which is the sum of both of those previous ones. And you have already seen the static equations, and already here I want to give a kind of a remark, which of course, everything is trivial afterwards when you think of it. But one difference compared to the traditional cases which we know is that it's, of course, the difference is between the streaming term, but what is something it's worth thinking of is that in the static equations, the delayed neutron precursor equations do not disappear. And that's a big difference, because in the ordinary transport theory or diffusion theory, when we look at the static equations, we don't need to bother with the delayed neutron precursors. We don't even give boundary conditions. I don't know if you thought of it. It's not necessary. And in a homogeneous model, the neutron distribution will be the same as the delayed neutron precursor distribution. Now I have to add something which you probably didn't think of, but the fact that in traditional transport theory, the delayed neutron precursors do not appear in the equations, it's already an approximation, but we usually don't think of it because this approximation is a very small thing. But the approximation assumes that the energy spectrum of the delayed neutrons is exactly the same as that of the prompt neutrons, which is not true. But the difference is so little that we don't bother about it. So we don't have delayed neutrons. We don't need to consider the delayed neutron precursor distributions. Here we do. And actually the distribution is not the same. Sandra already showed yesterday that in a static reactor, in a homogeneous system, they are proportional. But then when you start moving the fuel, then there will be a difference, and there will be a distortion, and so on and so on. And so that's why we have to keep them even in the static equations. And this is the boundary condition. So that means, that's again a repetition from several of the talks yesterday, we don't solve the equations in the outer loop. We just assume that the delay neutron precursors will decay, and then they will return with a reduced amplitude into the core. And then this is described by this decaying term here. Now, one can write also the static equations in a matrix form, if you like, in which then the neutron flux and the delayed neutron precursors are the components of the vector which we have to solve. So the time-dependent equations, you have also seen them yesterday. The only difference is compared to the static equations, apart from the time derivatives, of course, is that the boundary condition looks different now, because now we don't, the flux and the delayed neutron precursors are time dependent. So what we have is that the precursor density at the inlet at a certain time t is related to the precursors which left the core sometime before. And that is a significant difference which will cause some interesting it will have some consequences. So now, the non-adjoint property of the static equations, once you think about it, it's again trivial, but it's still a very interesting thing. Namely, what we know is that the transport equation and the traditional transport equation, and even the multigroup diffusion equations are not self-adjoint. It's only the one-group diffusion theory. Even the P1 theory is not non-adjoint. But now I'm talking about one-group diffusion theory model, and still the equations are not self-adjoint. And the reason is very simple if you think after. Usually, the condition of an equation to be self-adjoint is that the underlying physics is invariant to time reversal. And invariant to time reversal, that sounds posh, but it's a very, you can illustrate it in a very simple way. You make a video of the process, and then you play the video backwards. If it is also a physically possible representation of the process, then it is invariant to time reversal, and therefore it is self-adjoint. And now we know that in the transport equation, if you make a video, then in the video when you play it forward, then you see that the neutrons are leaving the core, and also in the energy they are behaving in a certain way, that fast neutrons slow down in small steps, and then when they become thermal, they jump up to the fast group in one single step. Now, if you play the video backwards, then you will see that there are neutrons coming in to the reactor instead of going out, which is not what they have for neutrons. But also, they will just climb up in small steps in energy, and bang, they jump down into the thermal in one single step, and that's not physical. Now, of course, the recipe of making the adjoint to a problem which is not adjoint is just reverse those terms, and that's what we will have to do here. Now, maybe I should have said, why is this at all interesting with the non-self-adjoint property? Well, the thing is this, that it is always convenient to have self-adjoint operators, because we know that the eigenfunctions of a self-adjoint operator are orthogonal. And therefore, it's easy to use a eigenfunction expansion to, say, time-dependent problem with respect to the eigenfunctions of the static problem, because we can find out the coefficients through the orthogonality relationships. Now, if the operator is not self-adjoint, then the eigenfunctions are not orthogonal. They are only orthogonal to the eigenfunctions of the corresponding adjoint problem. So that's why this is interesting. So if you want to use the theory, then we need to construct an adjoint operator to the direct operator. And also, it came up yesterday that the solution of the edge joint equation is what we call the neutron importance. Actually, there are many different ways of deriving the edge joint equation. One of them is what I will going to show here, is that you just define what is the condition of being a joint, and then you see how you can make the equation to be fulfilled. There is a better way which doesn't fit in here, but that's my favorite, is that if you take a subcritical system, in a subcritical system there is always a Green's function, which means that you can calculate the neutron flux in a point due to a source. Which means that then you have two sets of equations, the final or terminal coordinates and the initial or starting coordinates. And then for the determination of exactly the same quantity, that is the Green function, there is a dual possibility. One can fix the terminal, one can fix the initial conditions and operate on the final coordinates, and that's the forward equation. But to solve the same problem, one can also fix the terminal coordinates and operate on the initial coordinates, and that's the adjoint equation. And that means also that the solution of the adjoint equation tells you how much will be the flux as a function of the initial coordinates, and that's the neutron importance. That is, depending on where you start with the neutron, you will have a different solution. So there is a physical interpretation to the adjoint, and therefore it's also useful for giving insight. Now, what I told you is that I'm not going to go into the details, just give you the outline, is that one can very easily show that the condition of the problem to be self-adjoint is that if we take two or four arbitrary functions, any flux function and the phi dagger here, which is still, say, a flux function, and a delayed neutron precursor distribution, and another one, which is denoted here by C dagger, but this is not yet the adjoint. Then the condition of the problem being self-adjoint is that if we take this operator here, then we can swap this vector and this vector and calculate this inner product, which is a scalar quantity, because a matrix operating on a vector is a vector, and then you multiply two vectors in a scalar product, it will become a scalar. And those two things should be the same. And they are not the same. Probably it's obvious, but you can follow the deviations. There are, first of all, the off-diagonal terms have to be swapped, because that's one of the points when they don't agree, but that's relatively simple. The cagey thing is that the one is that the term corresponding to this one, that is the gradient operator, combining, I have to go forward, combined, putting into the scalar product, we show that what we get here is that this term should be 0, but it's usually not 0, because why should it be? There's no. Now, again, to make the problem not self-adjoint, but to construct an operator and a corresponding function, which is the adjoint function and the adjoint operator. One both needs to define the adjoint operator, and it's not enough to define only the operator. We know that from ordinary transport theory. One also needs to specify a different boundary condition. And so this is the same here. What we have to do is that, of course, we have to play the video backwards. So what it means is that we have to reverse the direction of the velocity. Now this is a scalar, not a vector, so it's only a sign. But also we need to define a different type of boundary condition. And that is the same as in neutron transport theory, that the boundary condition for the flux is that there are no incoming neutrons at a free surface. And the boundary condition for the adjoint is that there are no outgoing neutrons. There are no outgoing, the importance is 0 for the outgoing directions. And of course, this is consistent with the concept of the importance. A neutron at the boundary of a reactor with the velocity outwards will not contribute to any of the neutron flux because it's leaving. Now that's the same here. Now we reverse the boundary condition and we say that at the adjoint precursor distribution at the inlet will not decrease compared to what it is at the outlet, but the other way around. So we change also the sign of this one, which basically means that if we lift this to the other side with a negative sign, then it just shows that this flow goes backwards, so that at the outlet it will be, the importance will be smaller than at the inlet. And basically in a homogeneous one-dimensional model like this one, this just simply means that the adjoint will be the reflected form of the direct solution. So if you remember the figures which Sandra showed yesterday, is that at the beginning means at zero velocity, that is the traditional case, then the flux distribution is the cosine and also the delayed neutron precursors, but then they become a little bit skewed to the outlet, the delayed neutron precursors. Now in the adjoint it's the other way around. They will be larger at the inlet, of course, because the importance of a delayed neutron precursor entering the reactor is bigger than the one which is leaving the reactor, since it will have more time to decay there. So that's the adjoint. And then one can show that if we define the adjoint operator, that is, we take the transpose of the matrix and change the sign of the velocity term both in the operator and in the boundary conditions, then what happens is that if we calculate the same term where we had this minus sign before, now we have a plus sign, and that means that this integral can be written as just that's the value of the product of these two functions and at the outlet minus at the inlet. And then because this clever way how we define the initial conditions will lead to the fact that those exponentials just cancel each other, so it's zero. But now, and that is one of the beauty of this, well, I think, the molten salt equations, that this will give us a certain difficulty when we come to the point kinetic approximation and the point kinetic equations, of which I was deliberately silent yesterday because I knew that I would have an opportunity to talk today anyway. Namely, if we, what I will show later on, but I can tell in advance, if we try to derive the point kinetic equations in the traditional way with factorization and orthogonality relationships, then doing that only for the core, so disregarding, like we did all the time here, what happens with the precursors in the outer loop, that will not be possible. And the reason is a very interesting difference between the adjoint construction for a molten salt reactor and for a traditional reactor. Because I said that we change the sign of the velocity, that's okay. And we change also the boundary condition. But the big difference is that in traditional reactor physics, we define an opposite velocity of the neutrons, or the directions over which we define the value, the boundary value of the flux and the adjoint is at the same point at the same time. And that means that this will work even in the time-dependent case, because it doesn't matter if the flux changes at the boundary. It's still the same flux. It's just that the direction has to be changed. Now here, it's not the same. You see, what we define here is that the flux, the delayed, of course, it's the delayed neutron precursors when we have to change the boundary conditions. What we define is that we relate the distribution of the delayed neutron precursors, but also the adjoints, at another point at another time. And that will destroy certain of the mathematical operations which we perform when we derive the point kinetic equations. So this is one of the differences. It's maybe minute in the sense that the contribution of the delayed neutron precursors usually is a relatively small contribution to the neutron balance, but of course when we are close to criticality, even the small contributions are very significant. And altogether, even if quantitatively something is not very different, but conceptually different, it's very good to be aware of it. So that's about the adjointness. Now, I want to show that in simple models, it is possible to make interpretation of what the certain terms of the equation mean. And of course, I guess your first reaction would be, Vado, I already know what is we have already, when we write down the equation, then we have to know what it is about. So of course, in the starting equations, which I showed you. But in many ways, and in many cases, what we do is, and that is done also in traditional reactor physics often, that we start with two equations, one for the neutron flux, which contains the delayed neutron precursors, and we have another equation for the delayed neutron precursors, which has the flux. But because in the traditional reactors, the delayed neutron precursors do not move, the equation for the delayed neutron precursors, it's a pure time-dependent equation. It has space-dependent coefficients, but it doesn't matter. We can solve the equation or express the the delayed neutron precursors in a certain point. We can express as a retardation integral of the history of the neutron flux in the same point. And therefore, in many cases, what we do is that we simply solve the equation, express the neutron, the delayed neutron precursors with the neutron flux, and then substitute it into the first equation, and then we have only one equation for one unknown. And that's simple, and this is what we usually, that's one way of solving the equation also for the molten salt reactor. However, in that case, the kind of transparency of the equation kind of little bit disappears, and that's where I thought that it's interesting to show that one can actually give a very nice interpretation of those terms. Now, I did not show the steps, but if one solves the equation for the delayed neutron precursors, or rather expresses the delayed neutron precursors as an integral over the neutron flux, then it becomes a little bit more complicated because of the streaming term. Now, it's not true that the delayed neutron precursors equations only have time. Now there is also space, and therefore, when we eliminate them, there will be space integrals. So after this elimination, in the static equation, we will have this Helmholtz-like term here. Of course, then the buckling is slightly different from what, I mean, numerically, from what it would be in an equivalent solid fuel reactor. And then we have two terms here. And there are several ways of solving it. One way is what Sandra talked about yesterday, is that you can expand the solution, even the static one, in the terms of the eigenfunctions of the corresponding traditional reactor. That is, there's simply sine, cosine functions, the Helmholtz equation without all these integral terms. There is an equivalent way. This equation in this very simple model, homogeneous, one group, whatever, it can be still solved analytically, but it becomes a little bit more complicated because now this is an integral differential equation. And there's always one sentence which I like to quote, but this is not so very relevant here, but there is a very nice book with the title Equations of Mathematical Physics by a certain Richards, and there is an equation, a chapter about the transport equation, which starts with the sentence that integral differential equations have a little bit more than Christend, meaning that we don't know anything about the unicity, the existence theorems, and so on. Differential equations are nice. But this is not so very dangerous, but of course it's a little bit more complicated because now the characteristic equation is not second order, but it's third order because of this term here. That's the term which makes it complicated. It's one interesting thing is that if we do this elimination, the boundary conditions are defined with a delay time which corresponds to the time it takes for the fuel to get back to the core at the inlet from the outlet. So actually that is the that is the tau L, which is the time it takes from the loop to get back. And after the elimination, it will be only the total transport time which appears. That's interesting, but just a coincidence. Now, one can find out, and I'm not going to go through all the details, or probably I just make an outline, to make an interpretation of what the first term and the second term is. What I did is that I just wrote out that these two terms refer to the flux, and this would be the lambda times c, and c is here. So apart from the lambda that shows here in the second line. So it's simpler to try to interpret what this equation means, how we express the neutron flux, sorry, the delayed neutron precursors as an integral in time and space over the neutron flux. And one can take the first step by saying that when we do the same solution for the delayed neutron precursors for the traditional equations, and I said it's just a retardation integral, that the neutron flux in a certain point is a exponential integral of all diffusions which happened sometimes earlier, taking into account that if it was earlier, then it decayed. Of course, if the system is time independent, then this is unnecessary a little bit, because we can perform this integral. I think I have it on the next slide, that this is the comparison with the traditional case. This is the equation for the delayed neutron precursors, and when we solve it, it looks like this. That's in the time-dependent case. Now, in the static case, there is no time dependence, so one could perform this integral. But I did do that on purpose, that I kept this integral there, because this is the way how to interpret the terms. If we know that there is a movement of the fuel, then it's not valid any longer. If you want to intuitively derive the same equation, then we know that although this equation could be written down even without solving an equation by some intuition, then we know that it will not be valid any longer that the delayed neutron precursor density in a certain point is as an exponential integral of the flux at the same point, because the precursors which were born at some time earlier, they were born at a different space, and we have to take into account this. So if we do that, then yeah, we just have to modify our integral, taking into account that the precursors which were born sometime earlier at a different point were born sometime earlier. And so if we put into that one and we don't take into account that our system is finite, we say as a first approximation, we take an infinite system in one dimension, then of course we have to take this integral from minus infinity to the point where we are, because everything which comes from that side of the reactor will reach this point sooner or later. And then we have this integral in this form. Now, but if you take into account that actually some part of the time the precursors were not generated because they were outside of the core, so that periodically there are times when they are not in the core, and then sometimes they are also again in the core, then instead of having an integral from minus infinity to the point where we are, we have to take this integral split up into two terms. This one is, I'm sorry, this one here corresponds to the actual cycle of the recirculation, that all neutrons which were born from the inlet to the point Z, and this is how it at one point they were born, and then there all the others which were born sometime earlier. Time comes in only because of the decay. So that then we have an infinite sum, and that goes from 1 to infinity, not from 0, saying that 1 means that these are the neutrons which were already born in a previous cycle, but they had time to go through and then come back again. And so there will be an infinite sum. Now this does not look like as the equation as I showed you, but it's very easy to see that If we make a Taylor expansion of this term here, then we get exactly the same result. So one can then simply say that in the static equation, we have basically two terms. This term corresponds to the last cycle, I mean the neutrons which were generated between the point of observation and the inlet in the last cycle, and then all the rest which were generated in the previous recirculations. Now, one can, based on this, make two further simplifications, and I will completely appreciate if you say, come on, this is already so much simplified, that why do you want to simplify even further? Yeah, because it gives insight. Also, it gives a possibility to kind of estimate the contribution or the significance of the certain terms. So there are two ways of getting rid of either one of these, the first term or the second term, by assuming the following. The first one is that assume that the outer loop is so long, or the recirculation velocity is so low in the outer loop that practically everything decays before coming back. And that means that then we can neglect this term. You can also see it on the equations if you take the limit. You take the limit u equal to 0, and then it will be very, very easily obtained that the first term can be neglected and the second will be kept. Now, this gives some insight. Unfortunately, it doesn't make much simplifications mathematically, because, as I told you, the characteristic equation of this one is still third order, because if you want to get rid of this integral, you have to differentiate, and then it will be a third order equation. And then it's a little bit more complicated than the usual Helmholtz equation that we are used to. But it gives some insight. And in certain cases, that could be actually a good approximation, which means that then one doesn't need to take a more complicated equation. Of course, this could have been written down in a much simpler way than first making a complicated equation and then with an even more complicated procedure show that you can neglect one of them. If you neglect from the beginning that there is no recirculation, you just set the boundary condition that there is no incoming delayed neutron precursors, and then you get the same term. So I'm aware of this. But the second one is a little bit more interesting, because if we take the velocity going to infinity or the recirculation time tending to 0, then things become much simpler. And that that's a very beautiful toy model, because everything is possible to solve in a very easy way, and then it gives insight. That's the main point. Of course, there might be objections that an infinite velocity means that then if the fluid starts moving with the same speed as the neutrons, then there will be a lot of other problems. Of course, the idea behind this, that, and then now I'm showing a slide which Sandra showed yesterday. Actually, the infinite, it's like always, infinite velocity doesn't exist. We can talk about the limit, and then the question is, what is the numerical value when we can already talk about that we are very close to the asymptotic value? And in this reactor, I think this is a small reactor, isn't that, Sandra? It's a relatively small reactor, but and I don't remember the loop length, but here you can see that when the fuel velocity is 50 centimeters per second, then the returning time is sufficiently short that a large number of recirculations take place before the delayed neutron precursors from a certain passage decay. And so you see here, for instance, the decay effective and the loss of the reactivity because of the movement of the delayed neutron precursors. It's up to 3 or 5 digits the same, and therefore this infinite velocity is not as crazy as it might sound, because one can get into the close. The condition is just that the recirculation time should be significantly shorter than the decay time, the half-life of the delayed neutron precursors. Now, what happens is then, if we neglect this first term, then the problem becomes very simple, because this one is a definite integral here, and that's a constant. Of course, because of the homogeneity of the equation, the whole solution is undetermined to a certain factor, but it doesn't matter. It's still a constant. And that means that this equation can be solved very easily. And that is valid even in the dynamic case when we come to the neutron flux and the other things. So that is a very nice toy problem. And as it was in the previous slide, it's even self-adjoint because there were pictures about or figures about this this limit yesterday. That at the beginning, the flux is a cosine shape, and also the delayed neutron precursors are cosine shape. You start increasing the velocity, and then this cosine shape of the delayed neutron precursors get distorted, skewed. It will be shifted to, the maximum will be shifted to higher values than the center of the reactor. But when the velocity becomes fast enough so that there will be a significant amount of precursors returning to the core, then this will lift up also at the inlet. So in the end, with the infinite velocity, the delayed neutron precursor distribution is completely flat. What does that mean? That the problem is self-adjoint, because if we mirror it, we have the same solution. So that's a self-adjoint problem. It's very nice, and the solution you can get in 2 lines, because that's an inhomogeneous equation. If you take this term as a constant, then the solution will be simply a slightly different. It will be still a cosine shape if we take the center of the coordinate system at the center of the reactor, minus a constant term, but the shape is very similar, and we will have a criticality condition. Of course, the solution is undetermined to a constant because it's a homogeneous equation in the sense that the flux is occurring in all 3 terms, and that's it. And even the static equation can be solved without this approximation. But I'm not going through. The way of solving is that we take the derivative of the equation, so we have a 3rd order equation here, and then there will be 3 roots of the characteristic equation, and then we expect them to be a complex conjugate pair and real term, and we can get back. Yeah, this is how it looks like in the general case, that when we don't have this infinite velocity, and we can get back the infinite velocity case. Yeah, it's a criticality equation, and the infinite velocity case can be obtained simply by assuming u equal to infinity, and then we see that then the 3rd order characteristic equation will be simplified into a 2nd order. So that also shows that yeah, this is the solution for the static flux in the infinite velocity approximation. Okay, so much about the static case, and I will spend some time on talking about the neutron fluctuations in molten salt reactors, and I guess I will need to explain why this is interesting at all. So I'm going to be a kind of give a little PR talk for neutron noise diagnostics and give some examples, so take it as an entertainment. So neutron fluctuations in an MSR, of course we know nothing about it. We don't have an MSR, but that's not a reason not to think of it, as I already said before. Why would be interested in the neutron fluctuations and neutron noise? Just because we extrapolate the experience with what we have with existing reactors. In the existing mostly light water reactors, neutron noise diagnostics have been enormously effective in many ways. It is a way of finding out the status of the reactor in a non-intrusive way. We don't need to interfere with anything. There are small fluctuations there all the time, and the dynamics of the small fluctuations obeys the same laws as the neutron transport itself. And in a power reactor, because neutron fluctuations can be divided into 2 groups, and even in a completely static, unchanged, constant reactor, there will be fluctuations which are easy to observe at low power, which have to do only with the statistical properties of a neutron chain. That is, it's a branching process. Neutrons born together will probably die together, which means that there will be a statistics which is deviating from the trivial, and we use that for measuring the reactivity, the Feynman-Rossi alpha method. That is only That exists in a completely unchanged reactor. But if we have fluctuations of some kind, vibration of a control rod, boiling in a boiling water reactor, temperature fluctuations in the water, all of them will affect the neutron flux. All those things are stationary random processes with a very small amplitude, so that one can use linear theory, and they will also affect the neutron flux, and therefore by measuring the neutron flux we can find out what is going on in the reactor. Moreover, this can be used for detecting anomalies, beginning anomalies at a very early stage when there is still no change in the static parameters, so that it's an indication. It's a very early indication that something is going to be wrong if we don't intervene and don't do anything. And in some cases, one can also use those fluctuations to monitor, for instance, reactivity coefficients in the normal state, like the moderator temperature coefficient, which can be also measured by intrusive methods, but they are costly and they take time, money, and so on. Whereas one can find out the MTC simply by measuring neutron fluctuations and temperature fluctuations, and if one knows how they are related to each other. So that means that this is a very useful thing. So as some kind of an entertainment, and let's see if I can put this slides working. I think I already told this. Technological processes lead to neutron noise. So measuring the neutron noise, we find out about the technological processes. We have a lot of experience of that kind in Sweden, but I have to give credit to the beginnings. This is something from the 1970s. The HIFAR, if you know how it is, if you probably have seen it, it's a very small reactor. The high flux isotope reactor in Oak Ridge, which has a fuel cycle of, I don't know what, 3 weeks or something like that, in which after which you have to change the whole core, because the core is one single fuel element. It's a cylindrical something. It's a very interesting. It's amazing. It's still operating. And then the burn up is compensated by withdrawing control rods. And then this is one of the very early cases. Then this is the auto power spectral density. That is the Fourier transform of the neutron fluctuations, or the square of the, it's actually the Fourier transform of the autocorrelation function, but usually we calculate it by just taking the Fourier transform of the signal and taking the absolute value. That's the Wiener-Khinchin theorem. And then usually most physical systems, the response will decrease with the frequency, because inertia, that's a very, very general physical thing. I will show deviations from this one. But basically, that's what happens is that there is a plateau when the response of the neutron noise is basically the same at all frequencies. That's a logarithmic scale. But then it turned out that in some measurements they found a peak at a certain frequency. And then the reason was a failed bearing of the control rod, which made that the control rod was vibrating, and the vibration is it's not exactly monochromatic, but it's concentrated in frequency around the resonance frequency of the damped harmonic oscillator. This is something which was observed also in at least the VVVR 440 reactors have a control rod which is completely different from the Westinghouse and the others, when the control rods are clusters of absorber pins replacing some fuel elements. In those reactors, like that's in Hungary, it's a big cadmium hexagonal sheet, and that's very vulnerable to vibrations. So that's one case when one of the control rods of this these 7 black dots represent the 7 control rods in a bank which can be or were partially inserted into the reactor. And then people had at that time already in-core neutron detectors anticipating that it could be good to have possibility for diagnostics. And then they found out from the same thing happened, that the peak appeared. But then in that case, because there were several detectors, it was possible to find out that this was the vibrating one. And if intuitively you tell me that, but it's very easy, there was a detector very close, then I can tell you neutron noise diagnostics is a little bit more complicated than that one, because this detector had the smallest response out of the 3. I will try to show you, if I have time, why this is so. So intuition is not always working as like that. If it had been a a blockage, a thermohydraulic oscillation at the same place, then it would have been the biggest signal in the closest detector. But vibrations generate a completely different type of noise. So, and this is another case which many people may know, that the core barrel or the whole core of a pressurized water reactor can vibrate. Of course, that's very much exaggerated because that's in the sub-millimeter range. And usually there are neutron detectors. This is one of the Ringhals reactors in Sweden, when there are 4 detectors at one horizontal level, and there are twice 4 detectors at 2 axial levels. And what happens here in this simulation, that if the core is vibrating, then one can, for instance, see that it's easy to find out because the 2 detectors, at least at that frequency, will be out of phase because of the vibrations. There are other vibration modes, like the shell mode, when the phase relationships are different. So there is a way of finding out. In this case, you don't need to find out where this happens because there is only one core, as in contrast to the neutron, the control rods. But there are other types of oscillations. This is a simulation of an event which we had in the Forsmark 2 reactor in 1998. But this is a simulation, so it's very clean, and then one has the values of the neutron flux in each point because it's calculated. And that is a lot more local. I will come back to that also. Because it's a local perturbation, it's a big reactor, and the big reactor doesn't behave point kinetically. But I also have some values of how the measurement, this is the measurement, of course it's filtered, and now we do not have the neutron noise in each point because we have detectors only in a number of points. Actually, I can show how many detectors. This is the horizontal cross-section of the core of a boiling water reactor in Sweden. And then you can see that there are a lot of detectors because there are 36 detectors horizontally, and in each detector string there are 4 detectors axially. So it's a lot of detectors in the boiling water reactors. Unfortunately, we don't have any in the pressurized water reactors. There are many many detectors, but those small boxes represent the fuel assemblies. So actually, it's quite a distance between the detectors in terms of how many fuel assemblies there are. Now, the reason of the type of oscillation, the type of oscillations here is that sometimes, I know it sounds a little bit crazy, but that's it. Sometimes at core loading, the fuel element doesn't fit exactly into the place, and that changes the thermohydraulic boundary conditions, which means to oscillations of the void content in this fuel assembly. Now we have a measurement here which shows that the reality is always not as nice and smooth as in the models, and that's the measurement from which one has to find out where is the the fuel assembly which is unseated. And from this it's not so easy to find out. It's intermittent, some detectors did not work, so the point which doesn't move here is not because there is no change, but so then you need methods of finding out how this and it just shows that was the unseated fuel element, this rectangular something here, and the method which we used guessed that it would be the neighboring one, which is not a complete guess, but it's quite good because it helps people to find out much easier if you know that look at the neighborhood of this element instead of this 800. I mean, when there is no time for doing it. So that's one case. As many of you probably know, is that it's also possible to measure the velocity of the two-phase flow in a boiling water reactor. I told you that there are 4 detectors axially in a detector string, and we have 36 detector strings. And if one takes neutron noise measurements in each detector and cross-correlate them, then one can find out the transit time, not the velocity, but the transit time. Because you take just the cross-correlation function, and there will be a maximum at the transit time. It's a better method to take the phase of the cross spectrum, which is the Fourier transform of the autocorrelation function. And we know that if there is a time shift or a shift of the argument of a function, then the Fourier transform will be the same as without the time shift, but with an exponential, e to the omega tau. Which means that the phase will be linear, because the phase is omega tau. Tau is the time delay, and this is the phase. Now it looks a bit messy here again, but basically that's a linear function. It's just that minus pi is the same as plus pi, so we fold it back so that you can plot it easier. So there is a linear phase up to a certain frequency, and you can see that here there is a larger value of the slope because it takes a longer time for the steam to pass between two lower detectors than up when the void fraction is bigger, so the velocity is also bigger. So one can measure the velocity, one can also find out if there is a deviation from the expected velocity, and then in some cases when the detector string starts to vibrate, the vibration actually will have different phase relationships, because here there is a phase delay, that's why the phase is linear. If there is a vibration of the detector string itself, that will add a component which is in phase, the same phase in both detectors, which means that there is also a possibility to find out if the detector strings are vibrating. And this is the last case. I'm very proud of it because that's my Hungarian colleagues who did it in the PAX reactor, in which there are in-core detectors. And from these in-core detectors, from the signals of the in-core detectors, they found out that there is a non-symmetric distribution of the flow velocity. And why I think that this is a feat is that in a boiling water reactor, to measure the velocity, that's not complicated, because the perturbation is big. This is boiling. There's water. I mean, water or no water, that's a big difference. Here, it's a minor temperature fluctuations which will affect the Maxwellian spectrum of the thermal neutrons. And still, it is possible to measure the velocity. And it's not very visible, but you see that there is a different color. The color is simply indicating the velocity. You see that there is a non-symmetric distribution of the velocity. It turned out that that's because there was a crud on the surface of the fuel elements. So by neutron noise methods, you can find out deposit on the surface of the fuel element. Now it's a kind of a funny part of it that because of this, one bought a washing machine for the fuel element, which failed, and that led to the fuel failure. So you can sometimes say that neutron noise is, it's advantages if you use it in the proper way, but that's a joke, that's a different thing. So anyway, what I tried to do is that yes, I did. That experience shows that neutron noise measurements and the knowledge of the character of the neutron noise, which can be induced by certain perturbations or even certain variables in the normal mode, how they affect the neutron noise, or what type of, what characteristics the neutron noise will show to a certain perturbation. And so what I'm trying to do is a kind of a PR talk, is that what I noticed is that despite of this experience, there is no kind of conscious planning of what type of neutron diagnostics we plan in the new reactor types. And the thing is that, of course, in a way you can say that this is too early. We don't have any reactors. We have more important points. That's true. I agree. This is kind of marginal. But once you fix the design, there will be not possible to put any more detectors in it. So for instance, in the Swedish pressurized water reactors, we don't have one single in-core standard in-core neutron detector. We have traversing in-core tips, which you can, or movable detectors, that's the name in the pressurized water reactor, which you can have at a maximum of 20 minutes in the reactor for different reasons. So it's very good to think of it, and even if we don't know what type of perturbations can occur. Now, this is my little bit simplified picture of the molten salt reactor. I think this will be something what regards neutron noise due to the characteristics of the propagating perturbations. That's somehow in between the boiling water reactor and the pressurized water reactor. In the boiling water reactor, it's a very large impact of the bubbles. Actually, you cannot even see anything else, just the noise of the bubbles. The pressurized water reactors, the small temperature fluctuations in the coolant, They induce very little neutron noise. But here we will have there will be inevitably inhomogeneities in the concentration of the fuel, for instance, and also change of the fuel fluctuations in the fuel temperature. Small fluctuations will have a bigger effect than the fluctuations of the temperature in the coolant. So what I think is that it will be interesting to do measurements of neutron noise. One can find out if there will be in-core neutron detectors or in-core thermocouples. That's more complicated because they are not so very well suited to high temperature and so on. One can find out, yeah, for instance, in the French sodium-cooled fast reactor design, there is absolutely no space for in-core detectors. We realized that we had projects for the Astrid reactor. All diagnostics will have to be done with the X-core neutron detectors, which is a handicap. So I think it's worth investigating the properties of the noise. Now I will try to jump over a large number of equations here and just first of all refer to one of the chapters we wrote with a colleague of mine in the nuclear engineering handbook, and you can look also the equations in the slides. What I will tell you, that's a flavor. That's the following. Neutron noise diagnostics is based on expressing the neutron noise as a function of the fluctuations of the cross sections, because in the end, anything which happens, boiling, vibrations, and so on, one can formulate it in terms of cross-section fluctuations. It's not always obvious or self-obvious, but that's doable. And then once we have this, then it's only a mathematical procedure. Is that we take the time-dependent equations, and then what we do is that we say that the reason of the time dependence is that there is a time dependence which I forgot to indicate in the, I did it here. For simplicity, I only assume that only the absorption cross-section fluctuates because it leads to simpler equations. Of course, the cross-section of the fission will also fluctuate. It's slightly more complicated, but absolutely no principal difficulties. And so without the fluctuations, there would be, of the cross sections, there would be no fluctuations of the neutron flux either. So what we do is that we split up everything to a mean value, that is something which is not dependent on time, and the fluctuations. And then we try to express the fluctuations of the neutron noise from the fluctuations of the cross sections. And because we assume that all of them are small, we neglect the cross products so that there will be no time-dependent quantities multiplied with each other, and therefore we can use a Fourier transform, otherwise we would have problems. And then we can get, after the Fourier transforming of the linearized equations and eliminating the delay neutron precursors, we get a very simple frequency-dependent equation in which we have an operator operating on the neutron noise, and that is from the diffusion operator plus the Fourier transform of the time derivative, so this I omega over V. And on the right-hand side, we have the cause of the fluctuations, that the fluctuations of the neutron flux. And we can solve this with the Green's function techniques that we say that we solve instead of a simpler equation when we have a Dirac delta here, and then the solution is given for the neutron noise as an integral over the Green's function. Now, the neutron noise diagnostics, 2 steps. We have to be able to calculate, to calculate this transfer function. And then when we have this, then we have to invert this relationship because it's very, very nice, very simple. It's an integral. But the thing is that we measure this, we can calculate this because this depends, I forgot to say, because of the linearization, this doesn't depend on the perturbation. That's just the static reactor plus the Fourier transform of the time derivative. That's known. So everything is known in this frequency-dependent complex function, and that's what we don't know. And so we have to invert it, and that's the art of how to do neutron noise diagnostics. Because if a mathematician looks to that's a Fredholm integral equation. If the kernel is bounded, then there is a unique solution. Yes, if you know the functions in all points of space. We don't know that. We have only a few detector positions, and then that's when the ingenuity comes in. You have to assume a form of the perturbation which only has a few parameters, and then you can guess those few parameters, like the position of a localized perturbation. So I just tried to give some illustration of how it is done in the ordinary, that is the classical case, that we have a simpler equation in which this frequency-dependent buckling has the frequency-dependent zero-power transfer function, and then we solve this equation, and we have this Green's function which can be calculated in a simple model, in a very simple. There is an analytical expression. Now, how this looks like, I will try to illustrate in a file which I wrote to one of my courses in this program Mathematica. And I don't know if you know it, but you don't need to have this program in order to read the file. It's like with the PDF. PDF means portable document format. If you want to make a PDF, you have to buy a program. You have to have Word or something like that. But to read it, you need the reader. The reader you can download. That's the same with the CDF. CDF means computable document format. By the way, I'm not employed by Wolfram and Mathematica, but I like this very much, and I'm just at the beginning, so I understand that it will be. But you will have access to this file, and now I will have to page up to the side which I want to show you. How does the transfer function? By the way, the point kinetic approximation means that we try to describe everything. I will come to that very soon. Only in terms of an amplitude function, and in the noise case, we split even the amplitude and the shape function into a stationary part and the fluctuations. So in the noise, we want to determine the fluctuations of the amplitude factor, which can be given very simply as the Fourier, this transfer function times the Fourier transform of the reactivity. So the behavior of this Green's function is important, and this Green's function looks like this, or the zero power transfer function. And that is something comment I can have to, but yeah, Sandra said yesterday. This is the amplitude, and that means that if we have a reactivity perturbation, which is a white noise, so that it's same amplitude at each frequency, then the response will be like this. Of course, when the frequency goes to zero, then the response diverges, because then we have a very slow perturbation, and we have a reactor in a supercritical state in a very long time. And then, for some peculiar reasons, there is a plateau. There is a plateau, and this plateau starts from the frequency in rad per sec, which is the inverse of the decay constant of the delayed neutrons, up to a higher frequency, which is the inverse of the lifetime of the prompt chain, including the time the neutrons spend as thermal neutrons. And therefore, this is very low for heavy water reactors, because they spend a lot of time, and therefore the frequency will be much lower. But that's and then this is the phase of the response. And it was said yesterday that delayed neutrons make the response slower. That is valid for transients, but for periodic perturbations, that is something very strange. I hope you can enjoy this. It shows that at a very low frequency, the response lags behind with 90 degrees. And that's what you have if there are no delayed neutrons in the system at all. Because we know that all the time the reactivity is positive, the flux goes up. All the time the reactivity is negative, the flux goes down. That gives you 90 degrees. So if there are no delayed neutrons at all in the system, only prompt neutrons, then the phase is a constant 90 degree. Now you have delayed neutrons, and suddenly at the plateau frequency, which is, by the way, the frequency at which the important perturbations happen, suddenly the response will have a zero phase delay. I hope you appreciate this. This is something you have to think of. Suddenly, the presence of delayed neutrons make the response faster. That's a little bit of a, yeah, that's a peculiarity. There are a lot of interesting things. I cannot page with that one. So this is how the G naught omega looks like, and now I go to the case. This is supposed to show, yes, this is supposed to show the dependence of the Green's function. Now that's the space-dependent Green's function on the frequency and the size of the system and the position of the argument of the Green's function, which corresponds to the perturbation. Now, here you see that for a very low frequency, the shape of this Green's function is like the static flux. That means point kinetic behavior. Now, point kinetic behavior is not good for diagnostics because we cannot say anything about the position of the perturbation. I'm now manipulating the position of the perturbation here by sliding, and of course then the amplitude will change, but the shape doesn't change, which means that if we have detectors in the reactor at a few places, there will be the response or the ratio of the detector signals completely non-sensitive to the position of the part. So we cannot locate anything. Now, if there is a very, very strongly space-dependent behavior, like in this local perturbation, which I showed in Ringkas, if you remember this, that's not good either, because then you have to be lucky and have a detector very close. So actually, the point kinetic component is, of course, if it dominates, then it's not good. But it's good if it is there, because in certain cases it's good. Now, if I start changing the frequency, then what happens is that this is a small system, 100 centimeters, and this is still a traditional system. Then, when the frequency increases, then we start see deviations from the point kinetics, and that's what you expect. The higher frequency, the less neutronically coupled the system becomes, and the response becomes local, and that means that now there will be a strong dependence on the position of the perturbation. So if you have two detectors at two edges of the system, then we can find out if we know that the perturbation corresponds to a, say, a non-moving perturbation whose strength is changing only, because if it is a vibration, then it's a completely different picture. And if the system is bigger, I will just bring it back to the zero. If the system is bigger, now I go up to, say, 250 centimeters, then it will become space-dependent already at a much lower frequency. So that's, of course, in one way it's trivial. A big system is deviating from point kinetic much faster. But anyway, so that's what the theory gives us. Now, I'm just showing the corresponding results for a molten salt reactor. First, in the infinite velocity approximation, because then one can still get very nice results. This is the equation done. Now there is this frequency-dependent term, and the solution will be very similar to what we had for the traditional case, but there will be an additional term, and also the value of the parameters will be different. And now for the interpretation, this is just a repetition that we often write the neutron flux in two terms. One of them is the point kinetic one, whose shape is equivalent to the static flux, and the rest. So if you take an expansion of the response into static eigenfunctions multiplied by time-dependent parameters, which you Fourier transform into the Fourier space, then the first term will be the point kinetic term. And so that's what I already used earlier when I showed you that at low frequency, then the response is now, here are results with a comparison between a traditional system, which is the black one, and a molten salt reactor system of the same size and as similar as possible to the traditional system. There are two differences. One of them, which I forgot to show, but I don't go back, this plateau of the amplitude of the response in the G naught omega is equal to 1 over beta, which is another very crazy thing, because those are the frequencies where the delay neutron precursors already cannot keep up with the perturbation. Yet, that's them who determine the parameter determines the amplitude of the response. So what this says to us is that in any reactor in which the beta effective is smaller than in a traditional reactor, the amplitude of the noise will be bigger. Now this will have a lot of significance. First of all, it will affect the possibilities of the diagnostics, because I told you the diagnostics, the success of the diagnostics often depends on in what ratio the point kinetic and the space-dependent terms are mixed. The other thing is that the noise amplitude will be much bigger, and if there are people here from Spain, they know that, and even Germany, there is a type of German reactors, this older convoy reactors, in which the natural fluctuations has become so strong that those reactors are not allowed to be run on 100%. And the explanation is still not clear why this happened. It's just that the fluctuation is so big that the safety system gives alarm signals all the time. Now, if it comes to that extent, it's not good. But on the other hand, I, as a noise expert, I'm very happy because it shows that the noise diagnostics in a molten salt reactor has good chances, because the amplitude is high. The other thing is that a molten salt reactor remains point kinetic at higher frequencies than a traditional system. That's not surprising, because we know that there is a coupling. And the coupling is represented by the fact that precursors created in one point decay in another point, and that creates a kind of... So if we go to even higher frequencies, then at very high frequencies, the two solutions, the traditional and the molten salt reactors, become similar. I have another picture which shows how the situation changes in a molten salt reactor. Now, this is only a molten salt reactor, and the same reactor, the only parameter which changes is the velocity. And this one, this corresponds to the Green's function in this reactor with static fuel, no moving. That's the traditional thing. It's already quite deviating from point kinetics. Now we start increasing the velocity, then it becomes more point kinetic, because this is the uppermost one is the highest velocity. And of course the amplitude also increases because the effective delay neutron fraction decreases by the velocity. That is, we lose neutrons. So that's what happens. If we look at the frequency behavior, then what we will see is that depending on the velocity, there will be some peaks, and that is corresponding to the reoccurring of the perturbation. But mind you, this is not a time, this is a frequency. So it's not the same as what you have seen yesterday when you saw on the time domain that there's comeback. That's what happens when there are small periodic fluctuations, and then they can come back. I think I will take the last term only in words, because that would be too much equations and time starts to run out. I say a very last thing, and I will show then a few figures. Now, about the point kinetic approximation, I think I have a summary in words in that one. In solid fuel reactors, we have a rigorous way of deriving the point kinetic equations by a flux factorization, which was, I think, first introduced by Alan Henry a long time ago. When there is a mathematical procedure based on orthogonality relationships, when one can derive the point kinetic equations, which express the behavior of or the dependence of the amplitude factor on time as a function of the reactivity. Now, why I call everything which I do here dynamics instead of kinetics is that one difference is that the Henry equations give you the reactivity in terms of changes in the reactor, and I consider this as dynamics. If you look at the point kinetic equations, you define an arbitrary reactivity perturbation ad hoc. You say it, that's kinetics. But if you have the reactivity as a consequence of something changing in the reactor, if you want to make a point kinetic calculation, of course we know that it's only an approximation because we neglect the space-dependent terms, but one can make a mistake if the reactivity is calculated incorrectly. That is one out of two things which happens with the molten salt reactor. So I just said it in words. The point kinetic component is basically a projection of the full solution into the space of the static function. The point kinetic equation is an equation which gives as a solution this projection. And quite generally, you cannot always grant that if you have a solution of a full equation, and you take a projection, you can construct an equation whose solution gives you this same thing. And that's what happens in a molten salt reactor. There is no systematic or rigorous or correct point kinetic equation, point kinetic equation. And it's shown in the slides, but I'm not going into details. Because of the difficulty I told about the definition of the adjointness. You need the adjoint function, and in this case, the time-dependent properties. So, to calculate the point kinetic component, the only possibility is to solve the full equation and then project it, and then you have the point kinetic component. Originally, the point kinetic approximation was invented because it was simpler to solve. So it sounds like a crazy thing. Now you solve the whole equation. Why do you want to get in the point kinetic? You have already the whole equation. Because noise diagnostics needs insight. What is the ratio between the point kinetic term and the space-dependent term? So even if we know the full solution, we need to know the components, and that's what we can do with a molten salt reactor. So this is shown in equations, but I'm just paging over and going to the last slides, showing the, this is the, what someone suggested yesterday. You can still define point kinetic equations that you assume that the shape function is equal to the static flux, and then you derive the corresponding equation. Then one will get a behavior which is described by this dotted line. It doesn't account for those recurring peaks. Whereas if you solve the problem fully and then you make the projection, then it will give those, the correct solution. Now, the last thing is that what is the response of a molten salt reactor to a propagating perturbation? Basically, and I think even the words will not explain so much, the main type of perturbation is something entering the core and propagating basically unchanged, even in boiling water reactors. The main thing is the propagation. We have, of course, more bubbles at the top than the bottom, but that's already a second order effect. The main thing is the propagation. So and that is described by this thing, that at a certain point, at a certain time is the same as at the inlet, corresponding time before. And then we give a certain characteristic type of noise, which, first of all, the reactivity effect of such a perturbation has very characteristic dips because it's a harmonic function. At a certain frequency, it's just orthogonal to the square of the static flux, which is in the expression for the reactivity. So, depending on the frequency, we will have a different combination of the point kinetic and the reactivity terms for such a thing. And so this is how the shape of the response of the noise looks in the reactor at a frequency when the point kinetic term is 0, and it looks nearly like the static flux. Yet, if you take a frequency where the point kinetic component is added, then suddenly it will look like this green line. The reason is that although the amplitude, the space dependence of the amplitude is the same for the two components, the phase relationships are different. So at this point, they are in destructive interference, and in this point, they are in positive interference. Such a thing is never observed in boiling water or pressurized water reactors because the point kinetic component is already too small. But there is a chance that in a molten salt reactor that could be seen because the point kinetic component will live longer than that. I think time is out, so thank you very much for your holding out.